In this lecture, we will talk about solenoids and the magnetic field of a solenoid. Solenoid is a particular device which is used to slow the flow of electricity in a current. It's an example of inductor and have many applications. With the invention of magnetic field, many development took place in use of magnetic fields. Solenoids, toroids are something which is used to control the current. In this lecture, first we will discuss the introduction of this topic, which will include the introduction of magnetic field, introduction of solenoids, and the concept of solenoids, how it can be prepared. We will also discuss expression for magnetic field and applications, possible applications of solenoids, as it has many applications the development of solenoids will bring. By the end of this lecture, the student will be able to describe the magnetic fields due to solenoid, Ampere's law, the law to calculate magnetic field, how solenoid can be constructed, how the field can be calculated. We will learn these things in this lecture. Solenoids inventions has given a lot of boost in developing many devices. The basic thing about the solenoid is it can give force without touch. So many applications have been developed on this. First, before moving to solenoids, we must have the idea of Ampere's law. Ampere's law is for magnetic field. This law allows us to calculate magnetic field from the relation between electric current that generates the magnetic field. According to this law, the integral of magnetic field density B along an imaginary closed path is always equal to the product of current enclosed by the path and permeability of the media. states that if we are having a closed path, the sum over the element of the component of magnetic field is always equal to the electric current multiplied by empty permeability. This is another form. Integral have many types. If we are talking about line integral, it means we are moving on the line. We have taken a loop and we are moving on the loop. We are moving on the periphery, circumference. If we are having a coil and we take the line integral to the magnetic field of the coil, then this line integral of magnetic field is always equal to mu times the current passing through that coil. You are passing the currents to the coil, so mu 0 I. Suppose the current is I, then the magnetic field that you are having B dot dl, this will is equal to mu dot I. Mu 0 is the permeability. Yes, that is called Ampere's law. And this law is the form of one of the form of Maxwell law. Maxwell corrected this law, and this is one of the four Maxwell equation. It is very important law in electrodynamics as it formed the foundation of entire theory of classical electrodynamics. The Maxwell corrected this and significantly because it tells us that the magnetic field appears when electric field are varying in time. Mathematically, this can be expressed as B dot dl is equal to mu 0 I. Here I is the current that we have discussed, that uh, particle may have some current, so this is our current, and mu 0 is the permeability. On the left hand side, dl represents that we had discussed, that integral, the dl line integral, and this is equal to mu 0 I. Here mu 0 is the permeability. In the case of magnetic field, we use the term permeability. In the case of electric field, we use permittivity. This is permeability of free space. The value of this free permittivity is 4 pi into 10 to the power minus 15 Newton per ampere square. B dot dl basically line integral of B in a closed path. Whether the coil is a regular coil or irregular coil, the Ampere's circular law holds true for all. It should be closed. I think you might be remember Gauss surface. In the case of electric field, we talk about surface, Gauss surface, and generally we use symmetric surface. Similarly, for magnetic field, we use a term Amperian coil, and the coil which is regular or irregular, but the answer will be same. With these equations, we can calculate magnetic fields and we can calculate the relation between the current. The importance of this Ampere's law is used. It is, it can be used when we cannot do so by applying the Biot-Savart law, or the Biot-Savart law fails because it is used as a symmetric way, and generally it is used when the current is constant with respect to time. Similarly, as is with Coulomb's law and Gauss law, Gauss law is easier to calculate, Ampere law is also easier to calculate. This law uses the Amperian loop. We have shown here, suppose a current is moving and we have taken a wire, current is moving through the wire. Now we have chosen a Amperian loop around this, shown here. This is our Amperian loop. The Ampere loop is one such that each point of the loop either be is tangential to the loop and is non-zero constant, or B is normal to the loop, or B vanishes. So either B is normal or tangential, or B is vanishes. Yeah. We use this law to calculate the field due to solenoid. Before calculating the field due to solenoid, first we will be aware of the second thing that is important is what is solenoid. Solenoid is a coil of wire. This solenoid acts like a electromagnet when a flow of electricity passing through this. Basically, solenoid is a generic form of a coil of wire used as an electromagnet. It is also refers to any device that convert electrical energy to mechanical energy using solenoid. This device creates a magnetic field from electric current and uses the magnetic field to create inner motion. It is shown in the figure, the solenoid. Normally we keep these loops very close to each other here, and these are the loops that we have drawn. We can also see this by, we can also draw like a solenoid like this. Almost radius is same, should be same. Uh, like this, we can draw like this. This is solenoids. Electromagnetic solenoids find uses all over the world. It's very useful. We use in speakers, microphones, both contain solenoids. As a matter of fact, a speaker and a microphone are exactly the same thing, reverse of each other. It has many applications. Creation of magnetic field. The common application of solenoids are to power a switch, like the starter in an automobile or a valve such a sprinkler system. Basically, as we have seen in the last figure, it's a coil of wire in a corkscrew shape wrapped around a piston, often made up of iron. We can take any hollow piece, hollow tube, and we can just create this. Electromagnets have an advantage over permanent magnet in that can be switched on and off. So here is the process of creating a electromagnet. A permanent magnet can be give you the magnetic movement all the time, but electromagnet have this advantage: you can switch on or switch off. It gives you magnetic field only when the current is flowing, as we have seen in the last. Because magnetic field is equal to is proportional to mu 0 r. So this is the advantage of the solenoid. Like all magnet, the magnetic field of an activated solenoid has positive and negative poles that will attract to repel materials sensitive to magnetism. In a solenoid, the electromagnetic focus the piston to either move backward or forward. Actually, whenever you switch on, the solenoid behaves as a magnet. Now you can use this property. To calculate magnetic field of a solenoid, we consider here a cross-section view of solenoid. Solenoid is wrapped on a hollow tube, we assume here. Now, assume the current I is flowing through this solenoid. The magnetic field is about the axis of solenoid. To calculate magnetic field, we have assumed a loop that is ampere loop ABCD. And by using this, we will calculate solenoid magnetic field. In this ABCD, BC and we can calculate magnetic field. Consider an ampere loop with sides A, B, C, D and integrate along each side. In this case, along BC and DA, the field is perpendicular to DL. We are talking about these two sides. Here, the magnetic field is perpendicular as we have assumed the magnetic field in the direction of acceleration. Along transverse sections BC and AD, the field component is 0. So this will not contribute anything. Now, the field along AB is B and there is no contribution from CD also, which is outside the. Let the field along AB is capital B. The relevant length of this can be written as L is equal to H. The number of turns per unit length, if we assume, is small n, then the total number of turns can be written as nh, because n is the total number in per unit length and total length is h, so it will be nh. The enclosed current can be written as I and H. I is the current in the solenoid and the total current will be I and H. So, according to Ampere's law, B is equal to mu 0 I. And in place of IE, we can write I and H. So B is equal to mu 0 I and H. And on the left hand side, since we are talking about H length, so BH we are using. So this will be cancelled out, and finally the B is equal to mu 0 and I. So the current will be mu 0 and I. Magnetic field can be calculated if the current is given mu 0 and I. Here you can see this current depends on two things: N, the number of turns, the current. So if you know the number of currents and I, we can calculate B. The direction of the field is given by right hand rule. The solenoid is commonly used to obtain uniform magnetic field. Not only uniform magnetic field, but it can control the passage of current. So to slow down to uniform, we use solenoids. A long solenoid is another term which is one which has larger long length in comparison to its radius. The radius is small as compared to length. The larger solenoid consists of a long wire wound in the form of helix, where the neighboring turns are closely spaced. So each turn can be neglected as a circular loop. The net magnetic field is the vector sum of the field due to all turns. And we know the N come into picture while we calculate magnetic field. But we should keep in mind that we always use enameled wire for winding, so that turns should be insulated from each other, because turns should be close to each other. If they are enameled, means coated with something, then it will not interact each other and the wiring will be insulated. The magnetic field inside a long solenoid can be written as B is equal to mu 0 Ni, where N is the number of turns per unit length and I is the current flowing through the solenoid. The magnetic field at a point at one end of the solenoid can be written as mu 0 Ny by 2. So we have talked about solenoid and application of solenoid. In this lecture, a long straight coil of wire can be used to generate nearly uniform magnetic field, similar to bar magnet. And that is why it has enormous number of physical applications. The field can be strengthened by the addition of iron core in the tube, which are typical to electromagnets. The magnetic field is concentrated into a nearly uniform field in the center of long solenoid. The field outside is weaker and lines representing the magnetic field further apart. Thank you. We will learn toroids in the next lecture.